Hello everyone. Welcome to one more session of live discussion. Today, our topic of discussion is AC power management sensors, and I welcome Mr. Suresh Dwivedi ji for this discussion. So, my first question is, what are the key parameters measured by AC power management sensors?
The AC power management sensors measure several key parameters to monitor and optimize the performance and the efficiency of the electrical systems. For example, voltage. It measures the electrical potential difference between the 2 points in an AC circuit. Monitoring voltage ensures it remains within safe operating limit for the connected device. Another parameter is the current. It indicates the flow of the electric charge through the circuit. Measuring current helps identify overload, faults, or the abnormal power uses. Third parameter is the frequency. It reflects the number of the cycles per second of the AC waveform. Most systems operate at the standard frequency, for example, 50 Hz or the 60 Hz. In India, it is the 50 Hz. And deviation can signal grid instability. And next parameter is the power. It includes active power, reactive power, and the apparent power. Now, the active power is the actual power consumed by the device to perform work. Another is the reactive parameter. Reactive parameter is the power used to maintain the electric and the magnetic field in inclusive or capacitive load. Next is the apparent power, kVA, normally known as the total power flowing in the circuit, a combination of the active and the reactive powers. Next important parameter is the power factor, normally known as PM. The ratio of active power to apparent power. A high power factor indicates efficiency energy uses, while a low power suggests inefficiencies due to the reactive power. Next parameter is the energy consumptions, kWh. Cumulative measurement of the power uses over time, essential for billing, monitoring, and the energy saving strategies. Next parameter is the phase angle and the imbalance. Important in the three-phase system to detect the load imbalances or the phase shift that could affect system stability. So these parameters help in the real-time monitoring, load management, fault detection, energy efficiency analysis, and the preventive maintenance, making them essential for the industrial, commercial, and the residential power management applications.
Okay, so explain the working principle of a current transformer and its uses in AC power savings.
Can you repeat the question, please?
Yes. Explain the working principle of current transformer and its use in AC power sensing.
Current transformer, normally known as CT, is a type of instrument transformer used to measure alternating current. It operates on the principle of the electromagnetic induction, where a varying current in the primary winding generates a magnetic field inducing a proportional current in the secondary winding. The primary winding of CT, means current transformer, typically has only one or a few turns and is connected in series with the conductor carrying the high current to be measured. The secondary winding, which has many more turns, is connected to a measurement or protection device such as an ammeter, energy meter, or the relay. The current in the secondary winding is a scaled down various of the version of the primary current, allowing the safe and the convenient monitoring and recording. So the transformer ratio, turn ratio, also known as turn ratio, determines the relationship between the primary winding and the second and the current. So, for example, suppose a CT with a 1000:5 measures that the 1000 ampere in the primary conductor will result in a 5 ampere in the secondary winding. Thus, the lower current can be safely handled by the standard instruments. So, current transformer are widely used in AC power systems for current sensing, metering, and the protection. They isolate measuring instruments from high voltage power lines, enhance safety, and enable the monitoring of large current that standard instruments cannot directly measure. In protection system, CTs help detect abnormal current condition like overcurrent or the fast enabling timely disconnection or to prevent the damage. So when we summarize these things, so we can say that a current transformer steps down high AC current to a lower manageable value for the measurement and the protection, operating through the electromagnetic induction and the ensuring electrical safety and the system control.
Okay, so how does a Hall effect sensor work in AC power measurement?
Question. A Hall effect sensor measures magnetic field using a Hall effect, which occurs when a current carrying conductor or semiconductor is placed in a magnetic field perpendicular to the current. This interaction produces a voltage, Hall voltage, across the material perpendicular to both the current and the magnetic field. In AC power measurement, a Hall effect sensor is used to detect the magnetic field generated by the alternating current flowing through a conductor. The sensor typically consists of the core and the concentrates the magnetic field, a Hall element placed within the field, and associated signal conditioning circuitry. As the AC current varies, the magnetic field around the conductor also changes. This varying magnetic field indices a corresponding Hall voltage in the sensor. So the Hall voltage is directly proportional to the strength of the magnetic field. So which in turn is proportional to the current flowing through the conductor. This signal is then processed to determine the instantaneous current value, which allow measurement of the AC current, including both its magnitude and the waveform. Unlike traditional current transformer, Hall effect sensors can measure both AC and DC current and provide galvanic isolation between the high voltage circuit and the measuring electronics. They are non-instrumental and can be integrated into the closed loop or open loop configuration, depending on the application's accuracy and the response requirement. So in summary, a Hall effect sensor works like a detecting the major magnetic field creating by AC current and converting it into the proportional voltage signal. It enables precise, isolated, and the real-time AC current measurement making it useful in energy monitoring, power supply, electrical vehicles, and the industrial control systems.
Okay. Okay, so how would you design a circuit to measure active, reactive, and apparent power in a single phase AC system?
To design a circuit for measuring active, reactive, and the apparent power in a single phase AC system, the process starts with the accurately sensing both the voltage and the current. First, use a voltage divider or potential transformer to step down the AC voltage to a safe measurable level. For current sensing, a current transformer, normally known as CT, or the Hall effect sensor, is used to detect the current flowing through the load. Another is these voltage and the current signals go through the signal conditioning circuit, usually involving filters and the amplifiers. This step ensures the signal are within the appropriate range and the quality for the further processing. Often, these signals are shifted to match the input requirement of the microcontroller or digital signal processing, normally known as DSPs, especially if the signal supply systems are used. After conditioning, the signal are sent to the analog to digital converter, which is also known as ADCs, which can be standalone or built into the microcontroller. Both voltage and the current waveform are sampled at the regular intervals so that their shape and the timing can be accurately captured. The microcontroller or DSP process the sampled data. It analyzes how the current and the voltage waveforms align with each other over time. From this analysis, it can be calculated active power, which is the actual power consumed by the load, apparent power, which is the total power flowing in the circuit regardless of how much is used, and the reactive powers, which represents the power that flows back and forth due to its inductive or the capacity behavior. And these formulas for active power, apparent power, and the reactive power, you can directly taken from the internet or any textbook. So the processed result can then be displayed on an LCD, stored or transmitted through the communication protocol like UART, I2C, or Wi-Fi. So this design enables accurate real-time monitoring and analysis to power in a single-phase AC systems, which is useful for energy management, efficiency monitoring, and the fault detections. That's all.
Okay, so how do you isolate high voltage AC lines while measuring the current or voltage in a sensor design?
Okay. Actually, in the sensor circuit design, normally known as SCD, it isolates high voltage AC lines, is a very crucial for the safety and the signal integrity when measuring current or voltage. So this isolation protects low voltage electronics and the users from high voltage hazard while ensuring accurate measurement. First of all, we discuss the voltage isolation. To measure the voltage safety, a potential transformer is often used. It steps down the high AC voltage to a much lower level while maintaining the waveforms safe. The transformer provides galvanic isolation, meaning there's no direct electrical connection between the high voltage and the low side. Alternatively, we can use optocoupler or opto-isolator. Yeah, you must use the isolation amplifiers can be used after the voltage is sensed and conditioned. These components transmit signal across the isolation barrier using light or magnetic coupling, further protecting the system. Another is the main important is current isolation. For current measurement, CTs or current transformers are commonly used. A CT wraps around the conductor carrying the high current and produces a small proportional current on its secondary side. Since there's no direct connection to the high voltage line, so the CT provides both isolation and the current scaling. Another method uses the Hall sensor, which detects the magnetic field generated by the current without making electrical contact. These sensors are inherently isolated and they can measure both AC as well as DC current safely. Another isolation is the digital isolation. When the digitized signal from the sensor need to be transmitted across the isolation barrier, a digital isolator using magnetic or capacitive coupling are used. So these allow microcontrollers or the monitoring system to receive the data without direct electrical connection. Next question.
Okay. 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 So, what are some methods to protect sensing circuits from voltage spikes or transients?
Actually, nice. Protecting sensing circuits from the voltage spikes or the transient, it is essential to maintain their performance and the longevity. For example, surge protection. Devices like metal oxide varistors, normally known as MOV, metal oxide varistor, and gas discharge tubes, GDS, absorb the direct excess voltage, protecting sensitive components. So MOV clamp voltage spikes while GDTs deliver large surges to the ground. Another is another protecting is the diode protection. So Zener diodes we use for protecting Zener diodes. So these diodes clamp voltage to a predefined level, preventing excessive voltage from the damaging the circuit. They are ideal for protecting lower voltage circuits from the transient spike. Another protecting device is the DVS diode, transistor voltage suppression diode, normally known as a TVS. So these diodes are designed to respond quickly to a voltage spikes, clamping them to a safe level. So they are commonly used in both unidirectional and the bidirectional applications. Another protecting device is the capacitors. Placing a capacitor across the power input helps filter the frequency transient, which absorb short duration voltage spikes. Ceramic capacitors are often used for the fast response filtering. Next is the inductor. Inductors combined with the capacitors can reduce the impact of the low frequency transient by opposing sudden changes in the current if it effectively filters out the voltage spikes. Another protecting device is the RC snubber circuits. These circuits consist of the resistors and the capacitor in series designed to suppress transient, especially in the inductive load, by dissipating energy as well as the controlling voltage spikes. Another detecting device is the grounding and the shielding. Proper grounding helps safety direct excess voltage away from the circuit, while shielding prevents external electromagnetic interference, normally known as EMIs, from the causing spikes. Next parameter, next phenomena is the fuse and the circuit breaker, normally known as CB. So these devices disconnect the circuit when excessive current or voltage is detected in the input. So it providing an additional layer of the protection from the sustained over voltage. So applying these, you can protect your appliance through this inductor, RC snubber circuit, grounding, shielding, using fuses, etc.
Okay, so how do temperature variation affect sensor reading and how would you compensate them from your design?
It is also playing very important role. Actually, temperature variation can significantly impact sensor reading. As most sensors have temperature dependent characteristics, so these variation can lead to drift in the sensor's output. So causing inaccurate in measurements. For example, a resistance-based sensor like thermistor or RTD changes with the resistance with the temperature, while the semiconductor sensors like MOSFET or photodiode experience changes in their electrical properties. So, if not compensated for, these effects can result in the unreliable data, especially in the environment with the fluctuating temperature. So what is the effect? Effect on the sensor's reading. So temperature will affect the reading of the sensor. For example, when thermal drifting is taking place, many sensors exhibit a shift in their outputs as temperature changes. This can lead to a non-linear response, affecting the accuracy of the readings. Another effect is the sensitivity changes. When temperature changes, its sensitivity changes. So temperature variation can alter the sensor sensitivity, meaning the same physical quantity, for example, pressure, light intensity, might be measured differently at the different temperature. Next affecting parameter is noise. Increased temperature can lead to higher thermal noise, especially in the electronic components. When temperature increases, noise increases. That is the reason. In case of the amplifiers are analog to digital and ADC circuits, it converts further, degrading the signal quality. And compensation method. Temperature sensors using an additional temperature sensor like thermistor or an integrated temperature sensor alongside the primary sensor allow for the real-time monitoring of the temperature variation. So the data from the both sensor can be used to correct the reading from the primary sensor through the software compensation. Another is the calibration. With the calibration, sensor can be calibrated at the various temperature to create a temperature compensation curve, which adjust the sensor's output according to the ambient temperature. Another is the active compensation circuits. Use of the operational amplifier, resistors, or other components in the feedback loops can actively adjust the sensor's output in the real time based on the temperature changes. Another is the temperature stable material. When you are using the temperature stable material, so sensors are the circuit components with the low temperature sensitivity can minimize the impact of the temperature fluctuation. So after incorporating these methods, it ensures accurate and the stable sensor reading across the varying temperature. So when we are designing the AC circuits, we have keep in the mind these parameters.
Okay, so how would you calibrate an AC current sensor in the field?
Yeah. Calibration is also playing an important role. So calibrating an AC current sensor in the field is essential to ensure accurate and the reliable measurement under the actual operating condition. Field calibration involves comparing the sensor's output to a trusted reference and the adjusting its response accordingly. This process helps eliminate errors due to installation condition, cable routing, or the environmental factors. So, to begin, ensure all safety protocols for the following, including the de-energizing circuits, where the necessary and the using proper personal protective equipment. The calibration setup typically include the AC current sensor installed on the conducting or precision reference metal, such as the true RMS clamp meter or calibrated multimeter, and the known load that can generate predictable current level. So by starting these, after knowing the AC load value to the system, the load should produce a measurable current within the operating range of the sensor. Use the reference meter to measure the actual current flowing through the conductor. Simultaneously, record the output of the AC current sensor, which may be the form of the voltage, digital data, or analog signal depending on the sensor. So, multimeter should be calibrated. When you are using the calibrated multimeter, your result will be accurate. So, another is the compare the sensor's output with the reference reading. If a difference is observed, they calculate the necessary calibration factor, typically gain, slow, or offset zero errors. For analog sensors, you may adjust the trimmer, normally known as preset or potmeter. So by using this potmeter to match the reference reading. For digital sensor, apply the correction factors in the firmware or those configuration interface. So repeat the measurement process at the different current levels, for example, 25%, 50%, 75%, and 100% of the sensor's range to ensure the consistent accuracy across the operating span. Once the adjustments are made, verify the calibration with the final series of the reference comparison and document the result for the traceability. So field calibration helps maintain the sensor's performance, and ensures data integrity in the real-world applications. So by applying these parameters, so you can get your correct reading after the proper calibrated, after using the proper calibrated instruments.
Okay, so to design a system to monitor and log energy usage in a three-phase industrial setup, what sensors and components would you use?
Okay. To design a system for monitoring and logging energy usage, a three-phase industrial setup. The goal is to accurately measure voltage, current, power, and the energy consumptions across all phases in the real time, while also ensuring data storage and the remote accessibility. The system would begin with the three current sensors, such as the split core current transformer CTs, are the real world coils placed on the real phase lines to measure current. In the parallel, voltage divider circuits or potential transformers would be used to the safety scale down line voltage for the monitoring. So these signals would be fed into an energy monitoring ICs like the ADE 7758, which is designed for the polyphase system and provide the accurate calculations of the RMS voltage, RMS current, active reactive operant power, power factor, and the energy consumption. So this IC ADE 7758 is very important IC. When you are using, so you can calibrate your system. So the metering IC would interface with a microcontroller or embedded processors such as ESP32, STM32, or Raspberry Pi for the data storage, area data acquisition, and the processing. So the microcontroller would periodically log, measure, and apply time standing using a real-time clock RTC module for the accurate timekeeping. For the data storage, a micro SD card or onboard EEPROM flash memory could be used for the local logging, while Wi-Fi, Ethernet, or GSM module can be included for the remote data transmission to a cloud server or the SCADA systems. An optional LCD or touch screen interface could display live readings and the system setup locally. To ensure the electrical safety and the noise isolation, opto-isolator and the proper groundings or shielding would be the implied. Additionally, TBS diodes and the fuses would protect against the voltage transients. So these systems enable continuous monitoring, real-time diagnostics, and the historical energy user analysis, adding the energy measurement, predictive maintenance, and the cost optimization in the industrial environment.
Okay, so my last question for this session. In a smart grid application, how can distributed AC sensors be synchronized and kept accurate?
In a smart grid application, synchronizing and maintaining the accuracy of the distributed AC sensor is very important for the reliable power monitoring, fault detection, and grid optimization. To achieve synchronization, each sensor node must reference a common time source. This is the commonly done using a GPS-based time synchronization. which is very popular nowadays, where each sensor node includes a GPS module to receive precise timing signal. The GPS provides timestamp with the sub-microseconds accuracy, enabling all sensors to sample voltage and current waveform at the same time across different grid locations. So alternatively, in case of where GPS is not feasible, network time protection protocol, normally known as NTP, or precision time protect protocol, PTP, means NTP or PTP, whichever is available, can be used over Ethernet or the wireless network to synchronize clocks between the sensor node as well as on the central server. PTP offers much better accuracy than the NTP, especially in the local network, making it suitable for the high resolution power measurement. So to measure, so to maintain measurement accuracy, sensors must be regularly calibrated against known standard and the use temperature compensated component to minimize the drift. High quality current transformer and the voltage divider RPTs should be selected for the consistent and the linear response. Each sensor node typically include an energy metering ICs with the built-in digital signal processing for computing RMS values, phase angles, and the harmonies, which improves measurement precision. Furthermore, implementing real-time clocks, normally known as RTCs, with the battery backup ensures continuity in the timekeeping during communication or the power failure. To correct for any clock drift, periodic time correction can be applied from the central server or the GPS source. So, finally, a robust data communication protocols and the error checking mechanism are the essential to ensure the data integrity during the transmission. With the accurate time synchronization, calibration, and the reliable communication, distributed AC sensors in the smart grid can provide the high fidelity data for the efficient grid monitoring and the control. So when you are very aware of these things, so then your grid will be better.
Okay, so that was a very brainstorming session, and thank you, Suresh ji, for sharing your thoughts. And if you have any questions related to this topic, you can share in the comment section. We will get back to you in next session. Thank you.
Thank you.